Oh, hello there. Hey guys, what's going on? Memes here. We're back. Don't mind the dragon Ouroboros in the background. I'm just saying that I just went up to my room at the monastery. I mean, unless you want to see all the hold on, let's take away from yes, all the random doors and closets. Which door goes to Narnia? That's downstairs, I claim. But, to not distract from it, well, aside from just a cartoon character like dude here, uh, welcome everybody, and today hold on, let me, get my professional YouTube other voice, talking in my ear. Hold on, pause that there we go, there we go. Alright, so we can tell we're actually connected, it actually works, and 'cause nobody's ever boomer casinoed on the internet. Not that I'm insinuating it, I love you, culture. Uh But I digress. So the moral of today's story is whilst at the monastery, and Mike had popped on the Discord for a little while, so we saw him there. I clicked on the Discord thing. I'm like, "Oh, let me pop him. Hey, what's going on?" Eventually, Thad joined in. They started talking. We got into some different conversation. Long story short, we started talking about Planck's black body radiation law. And okay, number one, it really confused me. I'm gonna say that I at least got to a point where I can at least do some equations and get out a number I recognize. I'm not saying I ain't still confused. I'm totally still confused, but I'm just saying it may or may not help knowing what the symbols on the documents and or equations mean. I learned that from Professor Feynman when he was at Los Alamos, where he's like, they're showing the blueprints of the Oak Ridge plant, and it's like very large blueprints all across the table and everything. And these couple of these engineers come in and they start explaining to Professor Feynman like he was a genius because he wasn't Professor Feynman at the time. He did not even have his degree. And they start saying, "Well, you see, Mr. Feynman, we had to make it sure there was no accumulation going on here." So they start going through the documents and they're like, okay, so the intake goes in here, goes up here, goes up and down, blah, 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 up and down, up and down. Very fast talkers, very complicated. And he said, worse. I don't know what the symbols and the blueprints mean. So, and ultimately, he waited a little too long. He's like, if you ask him right away, it's fine. But you waited a little bit too long. Now it's like, what are you wasting all my time for this time? So it's reading the words about what you're actually solving for rather than just being like, oh, I know those things. Oh, let me plug in Planck's constant here, blah, blah. What am I actually trying to do? Perhaps the solid angle and steradians matter. Those damn dimensionless things. What the heck are we even talking about here? All right. AKA something, probably luminous intensity might be, well, intensity might be another time in the denominator, but I digress. Okay. Welcome, Tony. Thank you. Thank you for being around. It's a fascinating thing, but all right. So let's get into what the heck we're actually what is all this jazz? What are we talking about? Okay, so let's do the laziest thing possible and just go to our thumbnail. All right. Share screen. All right. We got a window, some blank black body radiation stuff. All right. What are we talking? Okay. So this is the general to be fair, I was mostly confused about the other equation, which you end up having the c squared down here, and then they have frequency cubed up here. And to be fair, we're probably not going to get into all that algebra because that took a while and everything. And as you can see here, Dad was going through canceling out all these things, canceling out all these things. Long story short is basically you end up, well, number one, the question, what the heck are we solving for? See, that's the thing. It's like, all right, we're solving for this b, whatever the heck that is there, but this is a lambda. In this case, this is a wavelength, aka we're solving for a length, often expressed as an inverse, or like 1 over a length. Cool. All right. But we're solving a wavelength in respect to what? Temperature. Okay, that's the whole claim of a black body radiation spectrum, which, if you even at least read the current Wikipedia article, and again, take it for what it's worth, is a conceptualized, idealized situation that we do not actually observe. Okay, it's a literal spherical cow. It's a spherical cow concept. Does this mean there's no such thing as like a real quote unquote radiating black body in the radiation stuff and everything? Does that mean it's just all gray bodies? Is that what's going on here? I don't know. Yeah, long story short is there does seem to be, to my non-quantum mechanical knowledge, is all right. We had the Rayleigh Jeans law. What's that? You models a thing, it goes up, blah 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 blah, and then all of a sudden, ultraviolet catastrophe. It's let's just show the the little thing, which who knows? Maybe there's a better interpretation. Ultra UV catastrophe. I'm trying to figure out the fewest number of words. Oh, okay. Oh, that's interesting. Is that a different one? Let's look. Okay, here we go. Here we go. The most generic Wikipedia thing. All right. Thank you, Wikipedia. All right, let's take a look at this beautiful bean footage. Oh, it helps if I actually share the right thing. All right, stop that. Boom. Bing. There we go. All right. So it's this thing here. All right, our classical theory. Basically, okay. Long story short is when they're modeling things, what if you're trying to get to 5,000 Kelvin? Yeah. You see, it kind of goes off to infinity. It's starting to asymptote there. It's like, wait a second, these things should be radiating infinity energy. Well, that does not seem to be the case. Oops, doesn't fit. All right. Then you had the Wien displacement law, which kind of like covered a lot of this, but the Planck connection, basically using Planck's constant and everything, is I believe, and again, somebody correct me if I'm wrong, this was basically a quote unquote hack. It's like, what would we need to fit the data? He found like, what's it, like 92 or something like that, 91.6 nanometers or something like that. And then he plugs in the numbers and everything. Long story short, that's how we got Planck's constant, which is like 6.6 times 10 to the minus 34 joule seconds. What is that? That's energy seconds. That's energy per unit of frequency. Okay. Oh, we're solving for like a frequency thing and everything. All right. So long story short is it apparently seems to solve this catastrophe. Fantastic. All right. Where do we go from here? All right. So let's go through. All right, let's stop this. Okay. I feel like I closed the window with absolutely everything in it. Hold on. This is why we have history tabs. Okay. So I'll bring up this one, and then we'll bring up this one. How about just black body radiation? Where was it? I know. It's one of those streams. God, what the heck is he doing? At least we actually went through it before. Okay. So, you know what? Instead of that, let's do this. Let's get not too fancy. Hold on. I mean, I need to back room and get myself psyched up. All right, we don't need any high resolution there. All right. Ultraviolet catastrophe. We want the black body radiation one. All right, so not imaging. Planck's radiation. Here we go. All right. Planck's law. All right, let's share this beautiful bean footage, shall we? All right. Planck's law, brought to us by our friends at Wikipedia. Let's do the window. All right, we got Planck's law right here. This guy. Oh, look. Not to be confused with... Oh. Look, it's showing the exact... I swear, I just looked for the image, and of course, I literally come back to the exact same tab. Or at least picture. All right. So let's go here. All right. Let's read the definition brought to us by our. Don't mind me lowering my. Oh wait, I have a volume thing on my computer. Never mind. There we go. All right. So let's read our definition here. So, according to our friends at Wikipedia, every physical body spontaneously and continuously emits electromagnetic radiation, and the spectral radiance of a body, B sub. Is that looks like a nu? Yeah, B sub nu. That's that little funky V. Uh, describes the spectral emissive power per unit area per unit solid angle and per unit frequency for particular radiation frequencies. Try saying that 3 times fast. I'm not going to try it. Okay. So the spectral radiation, oh, this, okay. So it's saying there's 2 things. Okay. So every physical body spontaneously and continuously emits electromagnetic radiation, and the spectral radiance of a body, B sub nu, describes the spectral emissive power per unit area, per unit solid angle, and per unit frequency for particular radiation frequencies. So, what the heck does that mean? Okay, so note note at least what the heck are we looking at here? What the heck is this thing? All right. This is a U. We got our new here because, all right, the whole, okay. Typically, you may have heard the things E equals MC squared. Idealized situation, you're quote unquote at rest, whatever that may or may be. We're not going to include momentum because we're going to keep it simple. Full disclosure E energy equals mass times the speed of light squared. E equals MC squared. Oh, what's the other energy equals? Well, that's uh, Planck's constant times a frequency. New. That little funky V. Okay. So in this, what the heck does this mean? Here's the thing. Unless I'm actually going through it, I remember doing calculus in college and stuff, unless that's really applied. Okay, we're differentiating stuff in respect to other stuff. Cool. Energy, what are we saying? We're saying that a mass, a rest mass, its energy equivalence is that mass times the speed of light squared. Speed of light squared in our standard units is about 3 times 10 to the 8. You multiply that twice. Okay. You get like 10 to the 16. That's why the mass energy equivalent of about a mode of dust, which is about the Planck mass, that's the energy equivalent in like a lightning strike. You want to talk about some wizardry? If you could completely convert the energy from a mode of dust, E equals MC square, that stuff, literally lightning bolt. That seems like a wizard to me. But that's, I digress. Those are personal fantasies. But okay. But basically, it's that whole why the heck can this black body or whatever you want to call it law basically an equilibrium situation, which probably is much more accurate to what we're saying here, because the claim is it would be in thermal equilibrium. I understand I'm using the same word to describe what I just said, already using the word equilibrium. It's in some form of balance there. Like all the energy coming in, it is being emitted at an equal rate. Now, remember, spherical cow, it doesn't actually exist. So that's not something we would expect to see in reality. So we're going to take that as a spherical cow and break it down into how it might actually work. Okay. So what are we talking about? Okay. Emissive. All right. So it sounds like we're emitting something spectrally. That sounds very light like. Okay. Kind of like the electromagnetic radiation being emitted. All right. You throw your turkey in the oven. The oven's at like God, what do you cook a turkey at? You don't want like 350? 350 for like a lot of hours. That makes sense. Okay, you throw your turkey in the oven. It's whatever temperature, but at one point, ideally, that turkey will end up being the same temperature once it's in full thermal equilibrium with the rest of the oven. Okay, if you're looking at thermally, it's all going to basically look kind of like the same. So I realize if you actually have thermal lenses, there's other factors there. And again, the standard conventional oven might not be the best radiative chamber. I don't know, maybe it is. Uh, but what are we talking about here? So we're talking about power per unit area. What are we talking about? All right. So think of a spherical kind of light bulb. You got your perfect light bulb. It's emitting the same style of light in all directions. How the heck that would work? Well, we kind of base stars and stuff on it, I guess. But but all right, you've got a spherical light. It's coming out. Now, this is the part I totally forgot about. I forgot to include the the solid angle. What does that mean? Think about you turn on your spherical kind of light bulb. You got your spherical light bulb. You turn it on, it's going to emit light in a spherical shell around it. Okay. Cut it off at like a fraction of like a light second. So you could literally imagine like the light has reached this far, but you start here, but now you're here. All right. So you're going to map from that body. Think about kind of like your literal light cone. Oh my God. You're taking the angle there, and now you are trying to account for like how much radiation have you emitted per unit of time, or was it we? Long story short, is I didn't account for that part, and nothing made sense. I forgot my 4 pi. These things happen, though. These things happen. All right. So long story short, is we're trying to relate a frequency with a temperature. We got our equation here. We got our h pi. We got our Planck's constant. Whatever our frequency is there cubed. We got the speed of light cubed right there. And then we got this crazy thing here. Yes. And I'm not gonna lie, at least going through with Chad and being like, okay, we're looking at this, but that was kind of going through an algebraic derivation, which we don't need to go all the way through. But some of it is in the thumbnail there. But there are some very interesting closed form equations that kind of come out because you got like the dimensional stuff on one side, and basically this is kind of like the shape space, so to speak. That's gonna how it's going to adjust that particular curve there, depending on these variables. But what the heck is these variables right here? Okay, this is Planck's constant as a frequency. So what that means is, oh wait, that's that extra famous equation aside from E equals mc squared. We got Planck's constant, h times nu, the frequency, which also gives us energy. Boom. All right. What do we got here? We got temperature. Temperature, yes, we're feeling hot, hot, hot. But if you multiply by Boltzmann's constant, that's the other magical thing that gives you energy. So Boltzmann's constant times temperature gives us energy, means this whole thing here is dimensionless. So basically, we are literally comparing frequency energy and dividing it by temperature energy. So we get a dimensionless relationship because technically, I believe, you can also set Boltzmann's constant to 1 if you want to deal with temperature. Fantastic. What's this? This is E. This is not the charge of the electron. This is the base of natural logarithms. It's Euler's number. Yes. Euler. Uh, so basically, this is the number E. And then you're raising it to the relationship between frequency and the energy associated with that, and the temperature and the energy associated. Okay. Well, then you're doing the a standard, whatever. We got a 1 here for a dimensionless thing. We're subtracting out 1. Okay, that's going to give us a number for our shape space here. Let's how should we do this? So, okay, here's the first one that really confused me. So again, you can relate these in other ways. So, okay, so this is power in relationship to power per unit area. Okay, so your power unit area, so that basically you're taking an angle from that spherical luminescence body, whatever that may or may not be, and you're basically calculating. Uh, okay, so you're comparing the temperature with respect to the different frequencies, whatever that means. Okay, because you're literally relating frequency and temperature right here. So this is for the spectral energy density. So energy per unit volume per unit frequency. Okay. Here's where I really messed up. It's energy for a volume, and now you're calculating that for the frequency of emittance because apparently that whole you shine a whole bunch of infrared light on maybe a substance. But you don't really see the things changing like it would. But if you start getting some ultraviolet light there, oh my God, even just a little bit starts doing things as emission. It's almost like there's quantized levels within matter and stuff. Oh, that sounds familiar. I remember that from like some chemistry. Very cool. All right. So spectral energy density per volume, and this is at a given temperature. So this is that equation. So now this is the spectral radiance. Spectral radiance again. I'm not a radiometer. Okay. Okay. So in radiometry, spectral radiance or specific intensity is the radiance of a surface per unit frequency or wavelength, depending on whether the spectrum is taken as a function of frequency or wavelength. Okay, so we're relating frequency and wavelength. The SI unit of spectral radiance in frequency is the watt per steradian per square meter per hertz. And wow, that's a lot of qualifications. Oh, it depends on how we're measuring things. Okay. So it's kind of like triangulation, except we're doing pentagulation there because they had a pentagon there. That's very cool. Okay, and then if we're taking it from a point there. Oh, per unit for particular radiation frequencies. Okay, so that was what we did before. This is spectral radiance. That's what we're okay. Frequency. Okay, because frequency or the wavelength. Okay, and then okay, I can see as long as you're getting enough data, you should be able to identify, and then if you're using spectroscopy, uh, to basically see what do we see oscillating here? Do we see water? Do we see hydrogen? Do we see helium? What type of elements? Seems to be like I don't know, uh, technological wizardry. Okay, frequency at absolute temperature. The absolute temperature measures temperature starting from absolute. Okay, so with utilizing uh starting from absolute zero. Okay, so assuming 0 degrees Kelvin. Oh, okay. That's why in the equations earlier we could set it to zero because, well, oh, that's why it works. Okay. I think that's why it works, and those are the words that seem to make sense because if we're relating a frequency to temperature, how do you figure everything else that's going on? Well, you got to set it to something if you're going to try to solve some equations. So, like the long story short is, you end up having most all the dimensions can cancel out, and then you end up coming with like what's it? E raised to the x divided by e minus one, maybe to the x, something like that. Uh, yeah. So Boltzmann's constant. Yeah. So it gives us energy. So it's the same thing here. So we got Uh, this is energy in respect to frequency. This is energy in respect to temperature. All right. Okay. And light in the medium or weather material or vacuum. Okay. The speed of light in the medium. In the medium. Whether material or vacuum. That is interesting. I wonder if I stole that phrase from there. The SI units of spectral radiance. Uh, B sub nu. So B frequency. Are watts per steradian. Okay, so watts, power. What is that? That's energy per unit of time, aka at least within the Wolfram Physics Project. A maximally integral observer outputs the Planck power. What is that? You're putting out a Planck energy per Planck time. How much mass energy in that is that? To be fair, if something's outputting the Planck power, that would put out the mass energy equivalence of Sagittarius A star, what was believed to be the supermassive black hole at the center of the Milky Way. It would output the entire mass of whatever the heck that is in like 21 seconds. It's estimated at about 4 million suns worth of mass. And it would output that in 21 seconds. WTF, mate? That's a lot of power. But I digress. What were we talking about again? Ah, yes, power, watts. Cool. Now we're multiplying it by, okay, this is kind of a little deceptive. It's multiplying by steradians to the -1. Okay. Long story short is, what are we talking about? Solid angle. Think about your spherical cow light. All right. Basically, that just means we're dividing by 4 pi. We're dividing by 4 pi, basically saying we're outputting like a solid angle, aka a volume of whatever. Radiance in this case, spectral radiance. Okay. And then we're dividing also, so we're dividing power by 4 pi and then an area, aka those little diagrams of we're mapping that area, that literal light cone. All right. But we're mapping it to its surface there because if we've got a ball and it's gone out so far, we're just going to map it to a particular limit. And when we're going to take that limit and we're dividing it by frequency. Okay. So that is the same as multiplying by time. Okay. Okay. So we're dividing by our frequency there to kind of break it up. Okay. And then when we're looking at its wavelength in respect to that, that's power divided by 4 pi, steradian solid angle. Basically, if you just got the light coming out, just that's what we're doing there. It's a solid angle, aka a volume, but we're only going to calculate for a bit because, well, that's basically all the information we're really getting. Um, and then where it's a volume. So power volume, power spherical volume, power divided by a spherical volume. Oh, so we're turning into a spherical cow. Oh my God, that almost is a spherical cow, except it's power instead of energy. Ain't that neat? But welcome, VCs. Yes, yes. Don't worry. It's not as terrifying as it looks. I feel like I'm almost at least starting to be able to decipher what may or may not be going on. The term B and U are used to relate each other by a factor of, oh, look, 4 pi divided by the speed of light in the medium. Since B, our body, is independent of direction and the radiation travels at speed c. Okay. Okay, so that's not the body. We're relating its solid angle of stuff. That's what it sounds like. The spectral radiance can also be expressed in unit wavelength instead of per unit frequency. Okay. Because, all right. So wavelength is typically 1 over length, and then, well, frequency is 1 over time. Number of photons emitted by a certain wavelength or the energy density in a volume of radiation. Energy density. Great. Well, the phrase it tends towards okay. So Planck's law, yada yada, is basically kind of the balance that seems to fit just right. Only empirically determined constants. Later showed that expressed as an energy distribution is a unique, stable distribution for radiation in thermodynamic equilibrium. Okay. An idealized situation as an energy distribution is of a family of thermal equilibrium distribution, which include the Bose-Einstein distribution, the Fermi-Dirac distribution, and the Maxwell-Boltzmann distribution. Wow. That must be why people like it. Okay. So, all right. Okay. So, long story short, we get here. So, we should be able to. Okay. Let's let's go through some of these, shall we? All right. So, how are we gonna do this? Okay. So first, let me. Don't worry. Don't worry. It's not gonna. I swear, it'll be okay. It'll be okay. Let's. Okay. Let's just do this. Let's just start from new. Okay. Let me. We'll bring a we'll bring a Wolfram Alpha tab. It's okay. I I'm going. Oh God. Let's do this. All right. So first, let's do the dimensionless part. Actually, no. We'll just do the normal thing. Cause I actually kind of know how to do it now. All right. So what do we need to do? All right. So hold on. I'm gonna cheat. I'm just gonna bring both the things over. There we go. All right. So here's what we need to do first. Let's do this beautiful beam footage. What are we gonna look for? We're looking for the distribution of frequency in regards to temperature. All right. So we need two Planck's constants, two times Planck's constant, a frequency cubed. We're dividing by the speed of light. Those are our dimensionful ingredients. What the heck do we get? All right. Don't worry, I don't actually remember it. I have it pulled up in another tab to the side. So two Planck's constant. All right. And then frequency. I'm just going to do this all in Planck units. So I'm just going to do the Planck frequency. All right. And that's going to be cubed because that's what it is. It's cubed for frequency or our nu there, that little funky V. And we divide by the speed of light squared. All right. What do we get? Okay. So we get kilograms divided by seconds squared. Those are some weird units. Interpretation, spring constant. Oh, or perhaps a force gradient, linear force density, stiffness, surface tension, tear strength, Graves tear strength, Peel strength, spectral radiant energy density with respect to wave number, cleavage. Basic unit dimensions, mass divided by time squared. Huh. That actually kind of makes sense now. Um, See, I'm just viewing it if it's a spring constant, and if we can get to the Planck spring constant, that might be kind of cool. All right. So, because the Planck spring constant is what is it? Just literally just Planck units. Planck mass. You just literally take the units that's just said right there, divide by Planck. Wow. Time squared. It's going to give you kilograms divided by seconds squared. All right, here's the Planck spring constant. It's just 7.488 times 10 to the 78 kilograms and divided by seconds squared. Okay. Again, I just spring constant. That sounds cool. Why? Spring, you got a mass on a spring. It's like, all right, it goes down here over a time, going up over a time, bada boom, bada bing. It's again, I am saying a whole bunch of things that I'm sure people are going to have problems. Please correct me. I'm a noob. I'm basically just a crazy person on the internet, just going through this, doing some calculus. The problem is if you have a little knowledge, sometimes it can be dangerous because then it's like, what are you actually saying? If you just don't know anything, it's like, I don't know anything. That's why I try to claim not to really know anything. Okay. So we got that. That's our dimensional stuff. So we're gonna do this on another piece. Okay, so what else do we need? Now we need this crazy thing here. This 1 over base of natural logarithms. Uh, Planck's constant times nu is frequency. That's frequency. So this is energy in respect to frequency. You got Boltzmann's constant temperature, which gives us energy in respect to temperature, and then we subtract 1. So here's as a quick preview of what's going to happen. Because let's just do that top part. All right. So we got Planck's constant. Okay. So what else do we have there? All right. Now we need to multiply it by a frequency. All right. Planck's constant. I'm going to multiply it by Planck frequency. Okay. It's going to give us a number. Okay. What the heck is this number? Oh, wait. Okay, no. It's giving us a lot of joules. That's energy. Okay. Note. Okay, note this is not exactly 137 micrograms. I almost lost my mind about this before. It's actually 136 point like 5 or 6-ish. Not 137. I know, I got my hopes up too. I know. It's not like you can post a number and expect people to understand what you're saying. But note, what is this? Okay, they're not showing the energy. This is actually more than the Planck energy, because we divide by the Planck energy. Divide, we're gonna get like 2 pi. Yeah, 6.28. Yeah, we're getting 2 pi. Because if we want directly like a mass energy equivalent, we just do the 2 pi factor comes because it's Planck's full constant. If you just put h bar in there, you'll get the Planck energy. So we should have 1. Yeah, we got 1 here. So, and again, factors of 2 pi amongst friends, as Professor Carroll may say. I wonder if this is where it came from. But okay. So long story short is we got these numbers here. All right. So now we're going to take that extra part of the little equation over here, just this thing here. We're just going to do Boltzmann's constant. That's what this is. And temperature. And we're just going to use the Planck temperature. So again, we're just typing in the magical words. So it's Boltzmann's constant. And then Planck temperature. Okay. And then we are literally taking the energy we get from respect to frequency and the energy we get in respect to temperature, and we're just literally dividing and seeing the ratio between them. I'm just throwing in Planck units just to see the easiest quote unquote spherical cow examples. You do Planck units. Oh, do you not want to do this for me? Oh, that makes me sad. Come on. Maybe I'm using too many magical words. Hold on. Let me throw brackets on. Let me make it explicit. Please just multiply these things together and divide. Let's see. There we go. All right. User error there. All right. So Planck's constant times the Planck frequency. Planck temperature times Boltzmann's constant. Bada boom, bada bing. Because the Planck temperature times Boltzmann's constant will give you the Planck energy. The Planck frequency is a frequency, aka it's a wavelength. It's wavy. At least it's a frequency of something, so that seems to inspire signage there. So it's got a factor of 2 pi. Okay. Well, actually, no. That's because we're using Planck's constant. Never mind. I withdraw my earlier statement. That 2 pi factor is coming from there. Because if we turn that into h bar, it's just going to be 1 again, just like before. Okay, 1. All right. We'll take our 2 pi. All right. So I'm just saying this because let's see if it will actually work. If I express it that way. E raised to this. Is it going to have a cow? Oh, yeah. Oh, wait. Wait. Do I need an extra bracket there? Oh, maybe it'll work now. Now it's good to yeah, there we go. All right. You're probably wondering, for those joining right now, what why am I taking the base of natural logarithms, aka E, relating it to these things, and why the heck is it saying 535? Coincidentally, that appears to be the Planckian dimension of Hilbert space, at least to my knowledge, because at least upon looking at some other things, whatever E to the stuff is there, it's supposed to be expressing the dimension of Hilbert space. I'm just using Planck units and stuff here. These are all equivalent to 1, except for basically this. This is equivalent to 2 pi. So we're just taking E and raising it to 2 pi. Why are we seeing 535? Well, just for user knowledge, Wolfram alpha does tend to round. And if E to the 2 pi is 535.49, that's not 5.1. I learned in elementary school, if you had 5 or greater there, you're supposed to round up. That's less than 5, so you round down. Hence why we get 535. Confused the bejesus out of me the first time I saw it. I'm like, WTF, mate, what the heck is going on here? All right. But let's continue. All right. So I'm actually happy that worked, because now that might mean we can do 1 over all that jazz. That's outside of the parentheses. We minus 1 over there. Are we going to get our shape term? Oh my God, it worked. I'm so happy right now. All right. What the heck is that number? Hold on. It's 1 over 8 pi to the 4th, I think. Don't ask me why I might. Okay, then I just got it wrong. Okay, I have no idea what that number is then. Huh. That's interesting. Wait, where did I go? Where do we get that from? Let's do it. Well, let me take off 1 decimal. Okay, it's 1 over. Okay, yeah, E right. Oh, it's E raised to the negative 2 pi. Or at least that's what it appears to be. Oh. Okay. Oh, because that's basically what we're saying, isn't it? Okay. Very cool. Let's hold on, just for my knowledge. 1 over 8 pi raised to the 4th. Okay, that's something different. Okay, I was only correct to 1 significant digit. Never mind. This is the welcome to my day. All right, where are we? Okay, so we got that part of that equation there. So basically, this is our shape space using Planck units. All right. So now we take that, and then we just basically multiply by this. Should be able to figure out what's going on. All right, let's duplicate that. That wasn't the term I needed, but that's okay. Take our shape term. Boom. I'll throw you over here. All right, and then we'll take all of this. We'll bracket this beautiful bean footage. We'll copy it. We'll paste it right over here. Space in there. Go Wolfram Alpha. Have I used too many characters? Is it going to work? Ah, okay. We got an answer, my friends. So again, we're at the spring constant, but we've got a shape function here. All right. So now I'm not gonna lie, I'm still confused right here. I feel like we might need a 4 pi factor. Let's throw in some 4 pi. 4 pi stirring. Maybe I need to divide. Hmm. All right. Okay, don't worry. I'm still confused here. Uh, let's do a trick. I'm going to attempt to figure out the answer. Why? Let's see what happens. Like that. Let's take our literal Planck spring constant, basically the number I'm trying to figure out what factor I'm missing here. All right, we'll divide by that. Now I probably have exceeded. Oh my god. All right, now I have a. How far off am I? Let's see. 47 over 2,000. All right. 235. 23. Level of accuracy. I do not know what this number means. Invert. What's it look like? Oh. Oh. Looks like kind of like 42. How accurate is this? Hold on. Let's. Because I was gonna say the Planck momentum squared is. Well, then again, that's this is a dimensionless number. Why would I even attempt to do something like that? I'm just trying to fill in the blank. Okay. So we got our stuff there. All right. So what happens if we get whack? No. As we multiply by 4 pi. Is there something obvious here? I don't see anything obvious. Okay. Oh, I apparently have managed to confuse myself again. Wow, that's a whole lot of words there. All right, let's take this hack off. All right, we've got that. Let's just double check our equation. All right. Two Planck constants. Got two Planck constant. I got the Planck frequency cubed. Planck frequency cubed. Divided by the speed of light squared. Divided by speed of light squared. And we got our 1 over blah, 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 blah. All that jazz. The exponential of that. E to the 2 pi. Oh, is that? Yeah, -1. Hold on. Do I have the right brackets there? Oh, let's take that off. Okay, so you got -1. Make sure this has to all be bracketed. Okay. So that's -1. Okay, the E is right there. Okay. All right. So frequency variable. Okay. Oh. Okay, angular frequency with that. Huh. I had done this earlier. Wow. Oh, very embarrassing. Okay. Let's go through maybe actually where was the first one? Ha, 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 ha. Yeah. Okay. That's why. Okay. I'm sorry. I again, you remember how I said it helps to know what the symbols on the blueprint or your equations mean? I missed the bus here. I forgot something. Remember, we're we're looking at the body's frequency in respect to temperature, right? Okay. What what is this actually saying? We go back to our earliest discussion about reading what the heck is actually going on. What the heck is that? B sub nu in respect to nu and t. Okay. We read it. I did not retain the actual definition. It's right here. Okay. What are we actually talking about? All right. So, which one is it? This guy. All right. So we're looking at that guy. All right. So, what are we talking about here? Okay, again. Here's the equation we're working on that I've confuzzled myself again with. KB, aka this guy right here, that's Boltzmann's constant. H, Planck's constant. All right, that's the thingy right there. C is the speed of light in the medium, whether material or vacuum. All right, we got C squared there. The SI units of spectral radiance. Okay, aka what are we trying to solve for? Rather than here's the thing. What are we even trying to figure out? The SI units of spectral radiance, aka this thingy here, are watts. Yeah. I remember I went through this whole bit highlighting how important this was and totally forgot. Watts divided by 4 pi and then an area. Okay. And then we're dividing by a frequency, aka the spectral units are watts per spherical Cal volume for this one. And then for this guy, uh, yeah, this one, the spectral radiance are erg seconds, aka energy action. Action because an erg is. Let me double check before I say words that aren't true. Erg seconds. Joule seconds. Okay, action. So 1 erg second is 10 to the negative 7 joule seconds. Fantastic. Angular momentum or action. All right. So basically, all right. So joules seconds. So joules per frequency. Okay. Yep. Joule frequency or joule energy per second per spherical steradian or solid angle. Okay, steradian. How much is going on? What is that angle divided by uh, an area or basically a length squared? You're dividing by area, and then you're multiplying. Well, then you're dividing by frequency. That's oh, wait a second. Negative seconds. Or time to the negative 1. Time to the negative 1. And then hertz to the negative. Well, that's just going to cancel out. So that's going to be action, solid angle, and that. Oh, is that why that happens? Oh. Oh, that's why we get a spring constant. Okay. Because this ends up basically, if you just do this Planck units, this is basically just going to be, if you did it in joule seconds, that's action. So basically you got H bar there. So you got action, mass area rate. Okay. So now you're subtracting an area. So it's just a mass rate. And now you're multiplying by a frequency. So you got a mass rate. And now you get another time component in the denominator, aka you get mass divided by time squared. Oh, that makes sense. And then we just need a solid angle. All right. Oh, I did I just need to divide by 4 pi? Oh god. I didn't even attempt to see if this was my error. Okay, that wasn't the error there. All right. Let's see. Where are we? Where are we? My AirPods are quickly running out of power. I feel like Ultraman. Time is running out. All right. So I'm just gonna go to where I had the answer earlier. Oh god. Hold on, don't mind me. I'm gonna close it. Believe the Oh god, so many things. Wow. Okay, I obviously did not know these things as well as I thought I did. All right, not that one. Oh god, did I just oh no. Oh no. Oh no. Hold on, show full history. I closed too many tabs and it moved out all the other tabs that had the actual answers. Where were we? Okay, all right. That stuff there, that stuff there. Oh, okay. So open this guy, open this guy. There we go. I think that's it. And that was 1 over 8 pi to the fourth, right? Okay. So it's all the dang arbitrary tabs he's got. Where? Hold on. Where we go? Like energy. Da, 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 da. Oh, did I not even do it the right way? Tab. Here I am, just the shortcut trying to get to the right thing. Okay, I think I just needed to take off the 2 pi here, and I think it may have worked. Nope, we're just back to start. We're back to start. Oh, if this was 1, is that what it was? I'm dumb, aren't I? Ah, 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 ah. Okay, so and that is set at 1. AKA if I used H bar instead. Okay. Let's simply let's wrap up with dividing by our solid angle, that dimensionless constant that we may or may not have forgotten. Oh, am I still off? Wow. Is it 8 pi? Wow. Did I just could did I just confuse myself and just expect this to be it? Because that was almost to it. 4 pi, or is it if I just take that off? Okay, that gives the Planck spring constant, but that's just going to do it by definition. I'm just canceling it out. Wow, I should have double checked myself. Well, at least I kind of seemed like I was knew what I was talking about for a little bit there. All right, let me just double check one more time. Wow. No, not that guy. History. Wow. Managed to close the one that actually had my. This is why we can't have nice things. E Planck's constant. Okay, yeah, we went over that. We went over that. Planck's radiation. Okay, it's 59. Is that the relevant guy? Wow. I totally confused myself. This one we checked. Oh, that was really close. Was this it? That was Planck frequency e to the 1. Oh, I'm terribly sorry. Huh. I had far too much confidence in myself. Was I taking the root of taking the square root of the whole as I'm multiplying them together? Oh, I had confidence. I was actually looking at it. Okay, we figured that out. Probably right about oh god, yeah, it was earlier. Planck. Let's see. I know, this is not terribly exciting. My apologies. Let's see. A constant e to the 1. Okay, I think did I just not assume it was 1? Or is this where I'm supposed to multiply by 4 pi solid angle? Huh. H+C. Temperature. Wilson's constant, Planck tensor. Okay. Did we not even go there? Wow. Okay, I think I'm just gonna regroup. Huh. This is terribly annoying. Wait a second. Why is there that bridge there? Oh, I just didn't touch it for. Okay. Well, I just went through in normal Planck constants, but okay, so that was 1 over blah 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 blah. Speed of light, blah blah blah. Take off the 2 pi, and what is the exact factor? Wow, that's scary. 2 Planck constant, frequency, speed of light. What the heck did I do? And that's there. Speed of light. All right, 1 over. All right, that. Oh, yeah, this might actually help. Let's. All right, I'll take that guy. Our Planck spring constant. We got that guy right there. All right. One last shot. This is all we got. All right. We got all that. What's our difference? It's going to be like 1.16, isn't it? And by that whole thing. Okay. I failed. I have failed you all. I will avenge my misgivings at a later date. So, with that said, I apologize. Wow. You lose one set of tabs where you had the right answers. Like, wait, how did I go through this again? I had the confidence I could redo it. Tabs beforehand really help, especially if you're not sure what you're talking about. And I'm like, I just learned that. I'm totally fine. Oh well. But that said, hey, thank you all for watching. Apologies for confusing everybody, but tomorrow's another battle. Peace out, everybody. Da-da-da-da-da-da.